just shared the link, right? I think let me just make it open because currently it's not. So just anyone with a link. Okay, yeah. So anyone should have access now. So yeah, I'm software engineer. It starts me said already. This is July. So right about since the start of this year, I've been spending majority of my time um in the ways of ML systems, right? So like I try to just do my bits in it, and for anyone who cares, um, I I did biological sciences in school, so my background really isn't what most people um are used to in professions like this. So yeah, we'll be talking about inferencing and the math behind inferencing. So as we all know, like inferencing is sort of the biggest thing we have right now in AI. And when I say I mean the production part of AI, like the parts that we all interact with. So as it stands currently, um, pipeline is split so let's say about 3 or 4 different sections. So we have the pre-training parts, right? Um, we have the training, which is where we sort of train our models, right? Pre-training involves you sourcing for data, putting them in the right shape, cleaning them, and stuff like that, right? And then there's also the post-training parts. So at this point, you've trained your model, and then you 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 still have some there's still a bit of things that you need to do to your model, right, to make it nice, to make it proper. So maybe if your model will be deployed to corporations, you and certain corporations have like governance standards that needs to be met, that needs to be respected. These are the things you do within post training. If there are things where GDPR, for instance, whereby let's assume certain jurisdictions have rules on how models should behave. These are the things you do within your post-training period. Um, if you want to take out vulgar words from your models, so you do a whole bunch of cleanup. Some people also call it fine-tuning, right? And now there's also the inferencing part, which is where we are interested in. And that is what lets you interact with ChatGPT or any of your favorite LLMs, right? And like this part is where it's where we really start to see economics of scale when we talk about LLMs. And in order for you to deploy your models and for you to make the best use of the GPUs you have, it's very necessary for you to understand, okay, what is the math behind these models? And like the cool thing about this is it is all math, right? And everything is deterministic. So we could looking at whatever model you have and say looking at the behavior, the specification, and by specification I mean, okay, what is the model dimension? How wide is the model? Um, the fact that it is math, you can basically like walk your way backwards, right, to first principles and have an idea, okay, given this case study or like given these business requirements, um, how do I need to deploy my models? Do I need 4 GPUs? Do I need 8 GPUs? Um, what kind of model, what dimension of model do I need? Depending on the GPU, okay, if I need 8 GPUs, what should be the what should be the specification of the GPU in terms of, okay, what should be the flop counts or what should be the bandwidth speed, right? What should be the speed of the interconnects? Interconnect just basically means, okay, the connections between multiple GPUs, right? How fast do they move data? So in order to make this decision, it's always you definitely need to do some basic arithmetic, right? And we're going to just touch on some of that right here. So that's why transformer math really matters. You could call it inference math because or transformer math. And transformers basically are like the backbone of what really makes LLMs today possible. So It gives you operational guardrails. You know, okay, depending on how big my model is, if I deploy it on, let's say, if I have a model that takes about, let's say it takes about 80 gig of RAM, right? Um, this inference math would let you know, okay, 80 gig of RAM definitely wouldn't run on, and it's like a model rather that takes 80 gig of RAM definitely wouldn't run on a GPU that's just 80 gig, because then you still need some extra space, right, for when activations are generated. So that is what inference math helps you with. And then there's also a part of cost optimization. It really makes sense for you to deploy a model like, let's say a 32B model, for instance, or a 1B model on a B300, like an NVL 72 GPU rack. So you have about like 72 GPUs in a rack of B300. It goes for about like $4 million. It's very stupid for, excuse my French, but it really makes sense for you to deploy something that doesn't even use up to 0.1% of the computing power. So inference math lets you um, make these decisions based on factual data, right? And that's why it's very important for all of us to, those of us who want to get into inferencing, right? So I think I've spoken a lot about that. Let's move ahead. So yeah, this is the anatomy of a transformer. Can you see my screen? I'm right now. So I'll just quickly breeze through this. So in a transformer, you have, it's divided into like sections, right? The first is you have the embedding. Embedding just basically transforms your inputs into a matrix that the LLM understands, right? And that you can actually perform operations on. So your input is whatever thing you ask ChatGPT. Embedding then converts it into a vector representation as a tensor, and then you have, so that's one layer, and then you move to the next layer, which is in this case, in the diagram I have, what we have here is our RMS norm, and this just basically lets you transform basically lets you transform your inputs, right? It does some kinds of, does some kind of cleaning up to your data, and then you have you have like your attention layer. We have different algorithms for running attention. In this case, this is group query attention. I wouldn't really go deep into this, but it's just a way to optimize how fast, it's a way to optimize how you compute attention, basically. So you have different types. There's multi-head attention, there's group query. Group queries is an optimization to it. And then you perform another RMS norm, right? And then you perform a feed forward. So within this feed, excuse me, within your feed forward, you do some projections there. So like you expand, and we're going to say that as we go down, just right. So and then there's another RMS norm, and then there's an output projection. As you can see, this has 32 layers. This example I use, I think this is a Llama 3, it's B model, right? So this yellow portion here happens 32 times. And what 32 times means is that time will be taken, and as tokens are generated, it also consumes memory, and it consumes HBM, if you're making use of an accelerator. So this is just a diagram that, this is a table that just shows you, okay, for a 3B, for an 8B model, Llama 3 8B has about 4,096 I mean, the width of the matrix. So if you can just visualize what a matrix looks like, for those, if you're familiar with it just tells you, okay, we have about 4,096. It tells you the dimension, right? It's 4,096. That is the width, and we also have the number of transformers, query, 32 heads. This will become really important to us. And then if you look at, we also have the feed forward neural expansion size, which usually is like 4 times the size of your dimension. So this is basically 4x of d. Um, and we'll say much more about that as we progress. Okay, so now the important metrics we really need to consider when we talk about inference math and serving LLMs is we really care about memory, right? And we really care about flop counts. And in memory, we are basically storing KV tokens. And KV tokens is gotten, we get KV tokens, um, we get KV tokens within the attention layer, right? That's within the cell box that we have here. As you can see, group query, that's where we get our KV tokens, right? And that consumes space. And it consumes space within HBM. HBM is just RAM for powerful GPUs that companies like Google and Amazon and Anthropic run, right? But if you have like a normal computer, let's say you have a gaming PC, they usually come with VRAM. And so that's like your commodity. It's kind of is the RAM you find in your commodity hardware that's similar to HBM, just say it that way. And then we also care about flop count. So we want to know, okay, how fast, how many computations can our GPU perform per bytes of data that is transferred into the GPU. And we also care about, okay, what is, because these GPUs are connected to each other, and you can imagine the connection as a highway. Now we want to know, okay, how fast do cars within the highway move from point A to point B? So you could use that as a mental model for the speed of interconnects. And yeah, so we're beginning to get into the some arithmetic here. So we have KV cache. Just know that a KV cache is gotten from, so you have an input, right? Earlier on, as we said, which is whatever question you ask to ChatGPT, and then that input is converted to an embedding, right? Then we then we then like extract even before I go there, let's even talk about what a model really looks like. A model comes with a set of weights, right? So we have the key weights, right? We have your Q, your K, your V, and we also have your embedding weights. So let me go back here. This is a very important diagram. So if you look at all of these items we have here, these things actually consume space within your computer. In fact, like when you add up all of these things together, that is what results into your model. So a combination of these things here, which are all weights, and all of these weights are derived during training, right? A combination of all of them is what um gives you your model. So we basically do some multiplications with our inputs against each of these items, or against each of these layers, right? So um yeah, we do a matrix multiplication against K, against our query, then against K, and when we generate a KV, um this is usually this is usually what's it called, the equation that is performed as at that point. So we have the number of layers. In the case of llama, we have about, I think this example I gave, it also states 2 layers, right? And we multiply that by the number of heads, and it's a matrix, right? Since it's a matrix, you have like your row and you have your column, and this other 2 here basically represents each of K and V, right? And this 2 here basically represents, okay, what kind of precision of weights are we dealing with? So when models are trained, they are trained, the weights are can be represented in different formats, right? It could be a 16 bits width, or it could be 32 bits. If it's 16 bits, it means it takes 2 bytes of storage, right? So the more floating points precision you get, the bigger the storage that it takes. And usually the bigger the floating points, then the higher the accuracy. But like there are much more sophisticated quantization methods that could even give you really, really good quality with like low precision, which eventually is takes lesser space, right? So this I'm very sorry. I tried getting latex here so like properly render these equations. I couldn't get on, so that's why this all looks wonky. But you have WK, you have WV, and this just basically shows you the shape of what the weights look like. So for K and V, it's usually D model by D model. Remember that in this example that we gave initially, um, the model, the width is 4096, and then the height is also 4096. And then one token. Remember again the inputs that we give to our models, right? So the token usually takes the size of your weights. So if you have 4096, then that token has to match the width of your model, right? So C token has just one row within your matrix. And now you can now then, so when let's assume what is the capital of France is a query, we can then break what is the capital of France into um each word will be represented as a row, and then they just stack up against each other, right? So each row within our matrix represents a token. Say that way. The next row represents another token, but they all have the same width. That is, they have like the number of columns is equal across them, and like because of that shape, right? We're able to easily make matrix multiplications with our projections because they match with the same. They have like the same width. And this gives us our flop counts. So flop count is basically, okay, how many operations um, do we need to add a token? So, and this is for a full pass. So a full pass means we are going through all layers. Um, so here represents the K and V, right? Layers is basically the number of layers that we have, and D is dimension, 4006 in this case. Wow. So okay, so one thing we should look at now that really like the two most important things when it comes to evaluating the performance of LLMs or inferencing is compute and memory. So compute is, okay, how many computations do we perform? Can GPU perform? And memory is um how much how much storage can our GPU accept. So we have compute speed here. This is basically the ratio between the time taken to process one token or a batch. If it's a batch, remember it means we are stacking multiple tokens, right? Where each token is a row. And then from this memory equation, it tells us the time it takes to stream one HBM to our SRAM. So say SRAM as the place where the actual matrix multiplication is being performed. Matrix multiplication basically just means doing just you take A and take B and you do a product between them. That's just all it is. And we want to know if it takes you so much time to stream your weights from HBM to SRAM, then that is bad. We don't want that. Just have that at the back of your mind. In fact, that's the most important thing here. You don't want your GPU to wait doing nothing because it doesn't have any data. The goal of we doing inference math is we want to put our GPU in a position whereby it has enough work to do, right? That's just it. So let's go to the next slide. Yeah, so now this is another very interesting part. And look, this graph, I would love to really spend some time here. We have the roof line analysis. So this, what we try to do with roof line analysis is, we try to estimate, okay, at what point, right, within our setup do we get the best performance, and that's what roofline analysis does. So there's something called math intensity. I love, some people call it arithmetic intensity, right? Well, I like to call it, and some call it math intensity, and that is just, it tells us, okay, what is the flops per bytes divided by communication bandwidth. So communication bandwidth is, okay, how fast can we stream from HBM to SRAM, and as we are streaming 1 byte, right? How many flops can be performed? Basically, that's what it is. So if you look at this, what I would say is the rich points, or even before I get to rich points, if you can see this diagram, on the y-axis we have the hardware peak flops per second. So if you buy a GPU, um, it comes with a value which tells you, okay, this is the when this GPU performs in peak maximum capacity, right? This should be the number of flops that it performs, right? And we are trying to maximize this y-axis. Then, if you then look on this x-axis here, we have inference algorithms. So basically, the thing about, as I said, the thing about GPUs is you want to give it enough work to do. But look at something. If you look at this line going through origin, it shows you compute growing, right? And then if you look at this horizontal line, it shows you memory bandwidth. Now we are trying to get to this middle point. But in getting to this middle point, let's assume in our setup, we only deal with we have so many users on our platform, right? And then we only accept one request at a time. Or let's just even assume we have one user and user sent what is the capital of France. But then we only try to inference one token at a time. Now let's assume that's set up to be algorithm A. The problem with this is we are not going to your GPU wouldn't be busy. Your GPU won't have anything to do because it computes that token very fast and very quick. And as soon as it does that, it won't have any work to do. So, but if you then keep moving, like you improve your inference algorithm or you batch your tokens. So rather than it's processing one token at a time, it processes 50, 100, 1,000 tokens at a time, right? You will then get to a point whereby you're able to stream as much tokens from your HBM, right, into your SRAM. And that point here is called the rich points, peak arithmetic intensity is achieved. So how you know that is you're going to get the flops per byte that's been given to you by your manufacturer. Um, and then you divide it by communication boundary. That says, okay, what is the rate at which we are transferring tokens from HBM to SRAM? You get a value. Let's assume we get 500 flops, right? It tells you that for every byte that is moved, your inference algorithm, your setup is able to perform 400 metric multiplications or 400 floating point operations. If it is performing less than that, it means your GPU is waiting idle. It's not doing anything. So at the end of the day, we are just trying to have a regime, we're trying to have a setup that ships enough tokens to the SRAM from the HBM. Basically, that's what we're trying to do. And we call that phenomenon compute memory overlapping. So you're trying to overlap the computations happening on your SRAM and the shipment of tokens to your SRAM from HBM. Basically, that's what we are trying to do. So okay, yeah. So I even had an example here. So if you have a B300, this is 2.5 petaflops in flop speed. So 8 terabytes per second in bandwidth memory. You divide that to get 437.5 flops per byte. So you have to perform 437.5 floating point operations for every byte. If that's not happening, sorry, yeah, you're wasting money basically. So I would just like to talk about a full pass breakdown. So like if so you remember this diagram, right? We're basically trying to like walk our way through this diagram. That's what we're trying to do by that's what I mean by the full pass. So in a standard multi-head attention, we have like um four we have like four different weights within the attention block. You have the query, you have the key, and then you have the value, and they all have dimension of D model. And when you combine them, this should actually even have one more. There should be WO here. So I didn't include that. But when you, so that should be 4. So when you combine them, you have 4g squared, 4 raised to the power of 2. And then there's the feed forward network. Um, what this does is it's expands your matrix. So imagine if you have, if the dimension of your matrix is, sorry, excuse me. So if the dimension of your matrix is let's say 4096, so the feed forward expands it by 4, right? And so it becomes really, really large. And then it's the down projection contracts it back. So the dimension that we started with, because then it doesn't make sense if your input token is coming in um at 4096 of width and you're expanding, right? The reason why you expand is to like isolate the features. And by the time you contract back again, and if you don't contract, it means there's an imbalance between your your inputs and your outputs. And again, and because all these models are autoregressive means that when you have one input, when you have an output, that output acts as the input to the next output. So you can basically say it when you type in something on ChatGPT and you ask it the question and you just start spitting and one answer or one word after the other. The last word that was spat out would then be used as an input to predict the next word. So if the dimensions are not equal, then what do we do? So that's why we have to like do the down projection back again. So by the time you sum your up and down, you get HD squared. And once you add that to what happens within your attention block, you get 12D squared. Um so this is where the up and down happens, right? And then this is your attention block. But in this case, remember, this is a group query attention. There's a difference between group query and multi here. This is faster. I just to point out again. Um, so okay, so then now remember we're talking about KV cache now. I'm going to see the importance of KV cache. If we don't cache, if we don't like cache our tokens, then it means that by the time we try predicting the next token, we'll then have to perform the metrics. So imagine that we've predicted over 10 tokens, right? By the time we want to predict the 11th token, without KV, without caching our KV tokens, we'll have to generate from token 1 to token 10 again. And that is not easy. Like that's a whole lot of time. In fact, that skyrockets your algorithm to the n squared. By the time you cache KV, you then you then um you then optimize the attention block to O of n. But then remember that if you look at this equation that we have here, we have 40 squared plus 80 squared, right? Which gives us 12D. And this 40 squared is just from our attention block. So at the end of the day, caching our KV tokens already gives us 1/6, which reduces our computational time really by 1/6. But we still have it this squared here, which we really can't like cache this. So work is still done here, but like we get a 1/6 um improvements. So so we have memory consumed here. We want to know, okay, how much memory does this consume? And as I said, depending on what's your precision is, if it's a 16, if it's a floating point 16 precision, right? That's 2 bytes. If you're 7, so usually ETB an ETB param, we consider one weight to be one byte, right? So if they tell you, okay, this the model you downloaded is a 6FP16 weight, then what that means is that it is times 2. You're just going to do multiply. If once you multiply, you get, okay, you say, okay, that is what about 160 gig, right? Okay, yeah, it's even written here. That's 160 gig. If it is FP32, then you do times 4. If it is FP8, then you divide by 2. Exactly. So this is the equation that lets us. So this is the equation basically that lets us compute how much one KB cache token will consume. So if imagine you have like a GPU of let's say 100 gigs, right? Let's use something that's a factor of 2. Let's say we have a GPU of 64 gig, for instance, and you are trying to save a model of 80B parameter. what that tells you is that it's not even possible, right? Like, but once you run the calculations, you see that there's not even going to be space. I remember that you even still need a GPU. Your GPU still needs to have enough memory that is bigger than what your weight will be, because once it starts running the model, you're going to generate activations, and those activations themselves also still consume space. So you this basically lets you know, tells you, okay, this is the size of GPU that I need to have. Um, so parallelism is one way that we can optimize the speed of our inference setup. Um, in this at this point, what we care about is, okay, then we know how big our models are. We know how to calculate um how much a KV token consumes, right? And we know the number of weights that we have. But if we have if we have a model that is about 80 gig, that is 80 gig. Um, we only have, let's say, a 24 gig RAM, a 24 gig VRAM GPU. That's not possible. We can't fit 80 gig. So what we do is we could shard those weights across a collection of GPUs, and that's what parallelism does. So if we have a 24 gig, we could get like um if you get 10 of those of 24 gig GPUs, then that's about 240 gig. And now we now need to figure out, okay, how can we distribute the work across all of these GPUs in order to get the job done? I have some, okay, so I would so we have, so one is pipelining, right? So if you're familiar with um computer architecture pipelining, like just your CPU pipelining, basically what it just does is you can pipeline instructions. You can put them one after the other. So imagine if like you're a server, right? And you have people like coming into your store to buy. Somebody wants to buy some rice. Somebody wants to buy some chicken. Someone wants to buy some. You already know what your clients want. Like if I want to buy rice, I'm most likely I'll be buying chicken with it, and I'll probably maybe getting a drink. So if all of these things are like placed in different parts of your store, you can just pipeline everything all at once. Because once you know that, okay, if somebody orders for rice, then they'll definitely order for chicken. So I could put the rice, the chicken, the drink, pipeline them all together. So once the request comes in, I just save everything at once. That's what pipeline basically does. That's the mental model behind that. So in this case, imagine we have like um we have a model with several layers, and then we can basically um we can basically, what's it called now, um pipeline these weights, right, within within our GPU. So yeah, layer 1 to layer 5 in GPU A, layer 6 to 10 in GPU B. So we're just pipelining the layers basically. We can't stop all layers. We can't stop the entire 10 layers within our GPU, right? So we put 1 to 5 in GPU A, 6 to 10 in GPU B. But then the issue is that while GPU A is computing the matrix, GPU B stalls because it needs the activation of from previous layers. And if you remember, this is how it is. So you have layer 1, layer 2, layer 3. By the time you get to layer 5, layer 6 won't be able to do anything because it needs the results from layer 5 basically. So that's like one downside of pipeline, and then it causes what we call GPU bubbles. Like your GPUs are not doing anything; they're just like sitting down there. And like I have like a bunch of equations here that tells you, okay, um, this is the total execution time that it takes, right? And then this is the bubble time when your GPU doesn't do anything. We do -1 year in order to account for the GP, in order to account for the, how would I put this now? So you have two GPUs. Um, if I am, imagine me as a GPU, if I'm performing my job right, when trying to calculate the bubble time, I'm actually working. So I'm going to subtract myself from um from the pipeline stages basically. So and then we have fraction wasted, which is the bubble time divided by execution time. Um, let's proceed to okay. Okay, yeah. So this is where this is what we are really even interested in, the tensor parallelism. So with tensors, rather than you splitting your models into sections, right? You actually all your GPUs would have a piece of each layer. So now imagine, let's just imagine, for instance, we have a model of dimension 12. You know, usually we've been dealing with 4096. If you're doing 4096, then each model will take 1024. Um, will take like a section of the weights of dimension 1024. That's so say matrix of with 4096, right? If we split it into four equal parts, that will be 1024. We can also split it into 64 different parts, but usually the splitting happens on a per head basis. So if you have your weights, the way these weights are designed is that they are like they are still like broken into smaller bits. And that gives us like an optimization. It gives us a means to like optimize computing weights, because then we can just easily stuff sections. We can easily compartmentalize each of the weights, each of the sections of the weights, each section of the weights within the GPU. So and they are segmented by the features. So it's not like you're arbitrarily breaking the it's not like you're arbitrarily breaking your weights from any points. It has already been defined when the scientists were training the models, right? So you can just break them out at a specific at their point of um at their point at their feature boundary. Yeah, let's put it that way. So that is how we split. So each layer, each GPU just takes like a head. So sit as each section that we are breaking out, consider that as a head. So a width could have about 64 heads, right? So take Llama 3.170B with 64 heads and a GPU of 8 RTX as example. So a transformer has to perform has most important sections, which is the attention layer that we've spoken about, right? And then we also have the MLP up and down that we spoke about, right? For the up projection, that's the one that expands. We divide it column parallel, right? Mind you, again, when like these 64 heads that you see right here, right? We also divide it column parallel or column wise, right? Then for the downward projection for MLP, right? We divide it row wise, basically. And we're going to see why we do that in a bit. In fact, the reason why we do that is just to make computation easy, right? That's the reason why it makes computation faster. Imagine you having 1 billion matrices. Just imagine a matrix of dimension 1 billion by 1 billion. You can't stuff 1 billion by 1 billion in a GPU, right? But if with the good thing about matrices that they have like properties mathematically, right? They have properties within them that lets you sort of shard them, break them into bits, and then you can combine them later together. So the distributive property of matrix multiplication allows you to do that. You can just easily you can look that up after this, and you understand why it lets you why it lets you do that. So once you split your matrices into different bits and like you throw them, okay, you throw one to Ogun State, you throw one to Abuja, you throw one to Bono, you throw one to Oyo, and they all compute. You can then sum all of them back together by performing an elements-wise operation, and you get to back your answer. So that's a good thing that matrices gives to us. So we have column-wise splitting of attention heads. So okay, yeah. So this. So I said we have the attention layer, which is, and then we have the MLP up and down. Then we want to now look at, okay, how do we split the attention heads? I said it initially that we split them column wise, and this is basically ideally this y here should be yi. I should be a subscript, and what I represents is just one instance of a GPU, right? In this case, if you look at what I wrote here, parallelizing the attention layer is pretty much straightforward. since the projections are divided per head. And we can just shard the weights per head, meaning each GPU has its heads. And so basically this is I starts from 0 to I equals to 8, basically. That's what it is. So this will also be xi and times wi. So x in this place is inputs, and w in this place is the weight. So now um we've we have a yi, and then we we then move to row wise splitting of the output projection, which is wo. And now in this, so this should also be yi and wi too, and z will be zi. And the thing about this is, hmm, the thing about this is we then, so like since we've been able to since each GPU, right, has been able to compute yi, what we then do is we communicate that result. Each GPU, right, communicates. They don't even need to even communicate their results. They just need to. So let's even read what it says. So next up is to shard WO row wise across the 8 GPUs, and then we must. Oh, I'm sorry. This um this shouldn't be here. So one thing again. Let me make something clear. So after this presentation, I'm also going to share another link of an article I wrote. So this entire presentation I'm having is actually even based on the article. So you can even have a much more deeper understanding of what we are trying to do here. So and we can then multiply the what we got from here, y, against a row wise section of wo, right? Now when we do that, there's one thing, it changes the dimension of our input of yi. It changes dimension. I remember the dimension has to be, it has to be what we know it to be, isn't it? It has to be 4096, which is what came with the model. Now what we are going to do is we are going to perform an all reduce operation. And what this all reduce operation does is that it's performed on each GPU to synchronize the partial sum in order to get the final output from W of the output projection per head. So remember we have 8 GPUs, right? And we just sum all of them together as the final. And then we move to the MLP layer. So in the MLP layer again, we are done with the attention layer, right? In the MLP layer, we have the upward and the downward projection. So we just need to perform the same thing that we did for the attention layer, right? So for upward projection, we do a column-wise splitting, right? And then for the downward projection, we do a row-wise splitting. And yeah, so for the downward projection, we split it in headways, and then we share it across all the accelerators to multiply against each input from the upward, and then it contracts back to the model. So I think I'm kind of run out of time here, but let's just, so we have this equation here that basically tells us how we shard these weights across our GPUs. So n in this place represents the number of, n in this represents the number of GPUs that we have, and 4 in this place represents, in a standard transformer, it has like 2 main components, as I said, the attention and the MLP. And in order for us to remember, we said we would need to like split these matrices, and in order to do that, there's like technically or programmatically, there's an operation called the all reduce algorithm. So there's one called the all reduce scatter, and then there's the all gather. So all gather, basically what it does is, I think it's all gather, I think it gets different inputs right together, brings them together, it gets different inputs from all the GPUs, all the results from all GPUs, brings them together, and then it shares the one result to everybody. So everybody now has the same output. While the reduced scatter, what it does is that it has an everybody has a piece of their own data, right? They split it into sections and into equal sections, and then distribute it to all GPUs for them to perform individually. Once that is done, Algada kicks in by getting these outputs from reduce scatter, combining it into one, and sharing it to everybody to have the same data. Basically, that's what it does. Um, so how does this affect communication time? So one thing is the more GPUs you have at some point, right? It wouldn't make sense for you to have like it gets to a point whereby the number of GPUs you have in your system becomes counterproductive. And in the sense that as we keep scaling, right, the math work decreases because each GPU would have like lesser job to do. So if before they were doing like 4x of the of 4x work, and then you add more GPUs, it returns to 2x. But remember, they all have to sync their outs. They all have to sync their results across to each other. But then it gets to a point whereby if you have so many GPUs, the amount of work that is done, even or the amount of work that is done becomes lesser than the time, right, it takes to communicate the outputs. At that point, it doesn't make any sense anymore, right? So you want to hit that sweet spot whereby you have enough GPUs to do enough work, and communicating the response or communicating the outputs of of each of these GPUs across all GPUs, right? Um, doesn't outweigh the benefits of the amount of time it takes for one GPU to get a job done. And that's what we call. So when a GPU or when your system, right, has enough work to do that it doesn't get stalled, we say that it is in a compute bound regime. So it has a lot of work to do. But when your GPU doesn't have anything to do and is always waiting for jobs, right, or is always taking time to sync outputs across each other, then we say that it's in a communication bound regime. So I think I'll just stop here. I think this is the end of my slide. I would love to take any question if anyone does has. I've spent over 40 minutes talking.
Thank you so much, Emmanuel. Thank you. Such a session. Please let's give Emmanuel a round of applause. That's such an insightful session. So if anybody have questions, please can you raise up your hand or just unmute the mic to ask your question. Okay. Emmanuel has shared the link he referred to earlier. I'll just copy it out too so that we can share it with the notes later. Okay. It looks like no one has
I feel bad.
Emmanuel. Thank you.
But the point of all this is sorry to interrupt you, but the point of all this, like if you are done with this and someone should ask you, okay, what's the thing here? It's that you need to figure out a way to balance the amount of work, right, that our GPU is able to do and the amount of work that is sent to it. So there has to be a balance. And in order to find that balance, there are things that we need to know about. We need to know what is the compute capacity of your GPU, how many flops can your GPU perform, right? We want to know what's communication bandwidth. So what is the rate of change or what is the rate of transfer of data from your HBM, right, to your SRAM, because SRAM is where the mathematics really happens, right? Then we'll also want to know, okay, what is the size of your model, right? If your model is big, most likely you're going to need a big GPU setup. You also want to know, okay, what is the floating precision? What's the floating precision of your model? If it's an FP16 or FP32, or if it's a single precision, right? That would also inform, okay, what size of GPU do you need? You would also want to look at what is the attention algorithm style. So if it's um if it's a group query attention, then it's you basically what's just to put it in a very simple way, it performs less amount of computations, right? If it's a group query, if it is multi-headed, then you're actually performing much more. So once you have all of these bits, right, you can basically put them together, and like it gives an idea, okay, this is the kind of setup I need to have, right? And I think with if you can just know that, and then you can on your own, you can even begin to research on things. But that's just basically it. We need our GPU needs to be happy. We need to give it enough work for it to do. We don't want it to be idle, basically.
If you have a thought to share. Okay, all right. Thank you. Thank you so much, Emmanuel, for that.
Yeah, thank you very much.
I mean, I take it as nobody has a question. Yes, the slide was shared, and it will also be shared later along with the link to the replay. That is for Olorundara. So without questions, Emmanuel, thank you so much. And again, this is the second time, and this is the second time we're having to gain value from you in this community. We do appreciate you. Thank you so much.
Thank you.
So if you will please stop sharing so that I can share my screen.
Okay. All right. Thank you.
Thank you so much. Okay, so since there's no question, we'll just move on. Please follow us on social media. That is on X, that used to be Twitter and LinkedIn. And now we're going to the announcement. Our community day is coming next month. If you were around last year, you'd know that we had a very valuable session, insightful session. A lot of planning has been going on since the beginning of this year into this. So we encourage you to please register and then clear out your calendar for on the 8th of August and come and join us live. There are going to be panel session, hands-on workshop, networking, and research. The theme really is building for the age of autonomous systems. So we just, let's just bring the community on site. Let's put a face, behind all of the voices that we've been hearing. Emmanuel also just officially inviting you. It'll be good to meet you on that day. So just encourage everybody to please come and share with us what you know. Come and be a part of the community at large. So please make it a date and let us all have a memorable session on that day. Okay, so going back to feedback, please would like to hear from you. I'm going to just be sharing the link to the feedback to the chat. Please fill the feedback form. Would like to hear from you what can be done better, what do you enjoy the most, how can we optimize these sessions for the best and for you to get most value from it, and also for us to know what our community value the most. Thank you so much, everybody. Thank you again, Emmanuel. Thank you so much. We really do appreciate your presence and for always coming whenever we call. We do not take you for granted. Guys, also thank you for coming out. We could have called a meeting and then nobody showed up. But this is possible because each one of you came out to listen. Thank you, guys. The replay will be shared along with the links that Emmanuel shared and the slide. Thank you, and see you at the community day on site. Bye.